Welcome to Spring LIB.
So here we have two sources of light uh, being fallen on a metal surface. So let's call those two sources to have wavelength lambda 1 and lambda 2. So lambda 1 is given to be 400 nanometer and lambda 2 is 300 nanometer. Now, after they fall on the metal surface, the maximum kinetic energy is measured to be 1.10 electron volt in case of the wavelength to be equal to lambda 1. So let's say the corresponding kinetic energy is Ke1 and that is equal to 1.10 electron volt. And we need to find the kinetic energy, the maximum kinetic energy corresponding to the second wavelength. Now, in order to do that, we will use photoelectric effect. So we know that maximum kinetic energy is equal to the energy of the source, of the fallen source. So that is H times F minus work function of the metal. And F is C over lambda, so we can substitute that because we have lambda given in the problem and not frequency, so that will save some time to first find frequency and then substitute here. So we can directly substitute lambda over here minus phi. Now, there are two methods to solve this problem. So, method one could be to find the work function using information from the first case where you have both the kinetic energy and wavelength given. So, you can find work function, so phi, and this is going to be the same work function for the second case as well because you are using the same metal. So the work function for both the cases has to be same. So once you find the work function, you can apply it to the second case and use this same equation to solve for the maximum kinetic energy for the second case. So find phi first and then find Ke2. So that is one method. And another method would be where you don't need to solve for the work function. So I'm going to follow the second method because I think this is relatively simple, simpler than with respect to calculations. This is going to be relatively simple than the first one. So I'll be using this second method over here so you get an idea of applying this method in other cases. So let me just write this same equation. This one, let me call this stars. So let me apply this equation to both of these two cases. So we have Ke1 to be equal to Hc. So these two are constant, so they don't change with wavelength or frequency. So they don't change with wavelength or frequency. So we have Hc, which is a constant, and then lambda for the case 1 is lambda 1 minus phi. So phi is the work function of the metal. So we are using the same notation. We will be using the same notation for both the cases because the metal that we are using is same. And then for the second case, Ke2, we have Hc over lambda 2 minus phi. So as you can see, these two are the different equations of photoelectric effect for these two cases, lambda 1 and lambda 2. So now let's subtract one equation from the other, uh, uh, taking care the corresponding sides. So we are going to subtract the corresponding sides of the equations. So Ke1 minus Ke2 is going to be equal to Hc over lambda 1 minus Hc over lambda 2. And since phi is the same in both equations, so that just cancels out when we subtract these two equations. So now from this equation, so let me just write that again. So Ke1 minus Ke2 is Hc 1 over lambda 1 minus 1 over lambda 2. So from here we can directly solve for the maximum kinetic energy corresponding to lambda 2 without having to solve for phi, which is the work function. So we don't need to solve for phi, and this is really going to be very useful for much complicated problems where you have more than one variable to solve for. So here we have just one variable. Maybe you will have two or three variables sometimes, and this method is going to be useful over there. Even over here also, this is going to be much simpler than the first method. So now you can directly substitute all the values. So kinetic energy is, for the first case, is in terms of electron volt. So we need to make sure that our H is also in terms of electron volts. So H that we will be using, the value of H, so that will be 4.136 times 10 to the power minus 15 electron volt. So this is the same H. So this is Planck constant only, but we have expressed it in units of electron volt and not in uh, joules. So that's why the value has changed now. And we did that in order for the units to be consistent. So, or you can also choose to convert the kinetic energy into joules, use the value of Planck constant that is in terms of joules, and then solve for kinetic energy, and that way you'll get this kinetic energy in terms of joules only, and then convert it back into electron volts if you wish to. So let's substitute the values. And one more thing that I need to tell you is, oh, so this is actually electron volt over per second. Now C could be in meter per second because we have lambda 1 and lambda 2 in meters. We will convert them into meters, meter per second. And now we can substitute all these variables over here and make sure you convert lambda 1 and lambda 2 into meters, and not, they should not be in nanometers, they should be converted into meters. So you need to multiply a factor of 10 to the power minus 9 to each of these two wavelengths. So let me just write the whole thing. So we have H to be 4.136 times 10 to the power minus 15 electron volt. Then you have C, which is 3 times 10 to the power 8 meter per second. Then you have 1 over lambda 1, which is 400 times 10 to the power 400 times 10 to the power minus 9 meter. Then lambda 2, which is 300 times 10 to the power minus 9 meter. So this equation can be simplified. So instead of directly going to uh, use the calculator, you can first simplify this equation a little bit. So 4.136 times 3 times, so we can take this power 9 out of this parenthesis, the square bracket, and use it over here on the part outside. So that will give us 10 to the power minus 15 plus 8. So we are basically adding all the powers of 10. So we have minus 15 plus 8 and then minus 9 in the denominator, which means plus 9 in the numerator. So that will give us a net power of 10 to the power 2 over here, and then we can directly go to subtracting the reciprocal of wavelengths. Now solving this, you'll get the kinetic energy to be, okay, so there is a sign that I missed. So here it's actually minus. So let me just check again. Yes. So this is minus, minus, minus. Okay. So now solving this equation, we'll get the maximum kinetic energy for the wavelength to be 300 nanometer, and that comes out to be 3.14 electron volt. And if you are wondering about how you got, how you got a higher value for K2 where you have a negative sign over here, then notice that this is actually going to be negative. This is actually going to be a negative value. So negative times negative will be positive, and your kinetic energy is going to be higher in this case. Thank you.